Hi, everybody. I understand this is session number 2, pattern recognition and machine learning.
Yes, it is.
Okay, and the papers that are going to be presented on 25, 24. Sorry, I'm supposed to be
The first one?
the chairman of this track.
No, I'm hosting this blog.
Okay. Okay, thank you. Bye.
Okay, hello everyone. This is session number 2, pattern recognition and machine learning. I'm Elsie, and today I'm gonna be your host. Let me know if you have any trouble with the presentation or the listening of this session. Please, if you have any questions for the speakers today, you can send them through the chat or wait at the end of the presentation to tell them personally using your microphone. Let's start with the presentation number 1, which is an efficient algorithm for irregular parent nesting based on genetic algorithm and greedy strategy. Is in the room Germán Martinez or Edward Andre Dura, Jose Luis Sanchez. Oh, Jose Luis Sanchez is here, right?
Good morning. Good morning.
Good morning. Are you gonna be presenting this paper today?
Yes.
Okay, let me give you, here you have, so you can start presenting. And let's start. You have 10 minutes, please. Try to code your presentation up to 10 minutes. And at the end of the presentation, we'll have 5 minutes for questions.
Thank you. Good morning. My name is Jose Luis Sanchez. I am in the University of Alicante, Spain, in the Department of Computer Technology. And I'm going to present you our research work, an efficient algorithm for irregular pattern nesting based on genetic algorithm and greedy strategy. First, I will introduce the word nesting. The term nesting. Nesting consists of given a quadrangular sheet or foil and a set of different shapes. The action which consists of that these pieces must be arranged on the sheet. The objective is to find an efficient arrangement of these pieces on the sheet with the aim of optimizing the sheet occupation. The method that solves this problem usually consists of 3 stages. First, to develop a suitable geometric representation of the pieces, trying to simplify the management of the irregular pieces and the sheet. Second stage, to develop a system for overlap detection. This is very expensive in terms of computational cost when the number of pieces is high. And third stage, to develop some kind of heuristic for an optimal placing of the pieces on the sheet. In our work, pieces are represented in DXF format as vectors. We use a semi-discrete representation so that the elements are decomposed into rectangles of the same size, which we call strips. The width of the last strip could be smaller than or equal to that of its predecessors. In this example, we can see that this strip in green is represented by 10 17 as the first segment and 6693 as the second segment. In order to represent the sheet material, we use fractional numbers ranges representing the vacation strips. When the process starts, there are no nested parts in the surface yet. Each strip in the sheet is initialized with the range between 0 and the sheet height. And the last row of the vacancy table represents the width of each strip. As an example, we have this free space in the first strip, which is represented by the numbers 86 to 200. With regard to the pieces, orientations of each piece are formed gradually rotating the piece through a fixed angle step from 0 to 360. Each orientation has its own vector with the same entities in format DXF as the original part, but changing the coordinate values due to the rotation process. And also a mirror effect can also be applied to the different orientations of pieces. Well, the process of vacancy search is a little long. Well, it's checked if the less it is checked if the leftmost strip of the piece finds a feasible position in the sheet. Proceed to check the rest of the strips of the piece, and the process is accomplished from the bottom left corner up and to the right across the sheet vacancy table. We can see in this example a vacancy search. The piece overlaps a predecessor piece, so the process must reallocate the piece so as to find a correct position. The same with this piece, which is out of the sheet. With regard to the allocation of the sheet of pieces, an orientation order is determined for each piece with regard to best OpenSea criteria. This is a greedy method. A genetic algorithm is used so as to generate new sequences of pieces. There is an initial piece allocation. In this example, first piece is piece 4, last piece is piece 5. There is a crossover and a mutation so as to test different sequences of pieces. With regard to the with the experimentation, different regular and irregular patterns have been used, and different values for this set of variables: number of generations, number of sequences in each generation, strip width composing the semi-discrete representation of pieces and sheet, and rotation angle. We use this architecture, an Intel Core i5, and for the sequence generation process, we use 10 chromosomes. The search process stops when the performance has no improvement after 30 consecutive iteration or generation. In the first case of study, we try to place 28 units of 5 irregular pieces on a rectangular sheet of 80 times 50 centimeters, and we use a rotation step of 45 degrees. This is the final occupation we achieve with our method, and we finally observed that the strip width of 2 centimeters was the best. In case study 2, we tried to place 31 units of 5 irregular pieces and the same a rectangular sheet of 80 times 60 and a rotation step of 30 degree. This piece which is indicated by the yellow arrow has a vacuum, a hole, and this is the final placement of the pieces. In this case, the optimal strip width was 1 centimeter. In case study 3, we try to place 35 units of 4 irregular pieces, and the rotation step was just 1 degree. In this case, we observed that the best strip width was 2 centimeters. The occupied surface was the same as strip width 1 centimeter, but the computation time was much lower. In case study 4, we will try to place 50 units of a single irregular piece, so no genetic algorithm is needed. And the seed was 140 times 80 centimeters and the strip width of 2 centimeters. And this is the final placement of the piece. We observed that the step rotation degree 1 and 45 were the best, with a best computation time for 45 degrees. We checked our method with a commercial tool, and this was the comparison. The commercial tool is CNC apps, is a proprietary solution. For example, in case 1, the strip width was the best was 1 centimeter. Our method occupied a lower surface, and the computation time was much lower. The same with case 3. In case study 4, we find that was the best rotation step was 45. Our benchmark, our method occupied best surface, and the computation time was much lower. With regard to our conclusions, we have proposed an efficient and effective method for the problem of nesting. A genetic algorithm is applied so as to generate the sequences of pieces, and experimental results show that our approach achieves good performance for all the sample tests. There are some future work we will try to find. As an example, apply a minimum gap between pieces so as to avoid some error when making the cutting of pieces. The elimination of redundant orientation in some cases, and that's all about our research work. Thank you.
Thank you, Jose Luis. Does anyone in the room have any questions for the speaker? Okay, I found your work very interesting, and I think it's really useful in the industrial area file. And I understand the genetic algorithms use functions to adjust the patterns. Did you try, or how much did you play with that function in order to find like the one you are reporting right now?
Sorry, can you repeat, please?
The functions, there are many functions that you can adjust for genetic algorithms. Which one did you try for this work?
We just try to use the mutation and the crossover. And we have to manage this rotation and crossover because not every sequence was able to be fitted in the sheet.
Okay, very good. Anyone else in the room have any questions for the speaker? Okay, I think that's it for the first session of this, well, for the first speakers. Thank you very much, Jose Luis. And
Thank you, Elsie. Thank you, everyone.
a good one. Okay, so the next speaker is presenting automatic classification of products in P2P marketplace. Is it here any of the speakers from this work?
Yes, I am.
Okay, thank you very much, Marcelo. You'll have 10 minutes for your presentation, and we'll have 5 minutes for questions at the end of the presentation. Please,
Okay.
can you share the screen?
Sorry, I can't find where to share my screen.
All right. There is a bar in the lower part of Zoom that has
Yes.
a green button that says share screen, or in Spanish, compartir pantalla.
Yes, but I don't see. Here. Okay. Can you see it?
Yes, we can see it.
Okay. So, okay. My name is Marcelo Armentano. I am from UNICEN University in Argentina. And with this group of researchers, we perform a project in conjunction with Región Global, which is an enterprise which owns an e-commerce platform with regional scope here in Argentina. Well, I will be giving a brief introduction of the problem, tell you about some, or show you some screenshot of the platform. Then I will define the problem that we were asked to solve, the proposed solution, some results, conclusions, and future work. Well, peer-to-peer marketplaces, differently from e-commerce platforms in which sellers may be companies, have the particularity of users playing both roles of sellers and buyers. So a user can be selling a laptop, for example, in the platform, and also looking for another laptop to buy. The problem that we have is that the company asked us to solve was that they want to have an automatic classification of the ads that the users publish in the platform, in which ads are published in natural language in some part, for example, the title and the description, and they have to choose among a large number of categories in which to assign the product. The number of categories is 858, so you can see that it's a very high number. And the platform has more than 150,000 users registered which trade their products. Well, this is a screenshot of the site. It's not like fancy, as you can see, in which we can see in this part the main categories in which the ads are classified, which are properties, vehicles, services offered by other users. And this is the buyer's view. And you can find the same categories here in the sidebar, in which these three main categories are mixed up with Other categories, for example, food and beverages, technology, home, furniture, and garden. So we take the approach of grouping all the other categories outside properties, vehicles, and services in only one category, which we call items or products. We can see how categories are then split into subcategories. For example, for food and beverage, we have freshes, beverage, desserts and sweets, prepared food. And then these categories can be also split in a third category. From the seller's point of view, the first task that a person who wants to sell a product or offer a service has to do is to select the category. So the system offers the seller different categories. When the user selects one category from level one, they can choose the category for level 2 and then level 3 if available. Each category has its own set of fields that the user has to fill to sell the product, and there is the final stage in which the seller can select the price, describe the product, and upload one or more images describing the product. In this work, we work with the title of the article and the description of the article to make the classification. And here, well, we have another example of the forms offered to the sellers for the properties category, the items category, and the services category. We can see that the fields are different, but all of them have a title and description that are the fields that we use in this project. Well, so what was the problem that the company has? Mainly the large number of categories that the site has to classify the products. So sellers have the problem that they have to choose among these categories, which is a very tedious and error-prone task because there are some categories that are redundant or ambiguous. So maybe the sellers make a mistake in which they select when selecting the category. The main problem they have was that the administrators of the platform have the task of checking manually the category selected by users to verify if the proposed category is adequate or not for the product or service offered by the sellers. This is also a tedious task, it's time-consuming, and slows down the publication process. Since until the administrators, there are 3 administrators in the site, check the publication, it is not available for the buyers to look for the items. And finally, for buyers, it's very confusing to find when navigating the tree-like category structure. It's very frustrating for them to find products that maybe not belong to the correct category. Maybe this is intentional when sellers put a product in another category to promote it, and some errors that the administrators cannot check. So the approach we took was to use natural language processing techniques to process the text that is available in the title and the description of the product. With these techniques, we represent this raw text in a form that is understandable computationally. And then we used classification techniques to learn and predict from this information the categories that might be associated to each ad. The dataset that the company give us consists in a larger number that is presented in the slide, but we make a filter of the information because in June 2020, the categories were restructured, so many categories assigned to previous ads may be that it does not exist anymore. So we only used the more than 30,000 ads published between June 2020 and August 2021. that was when we started performing this project. And as I previously said, there are 858 different categories available. So the process that we do to the text, it was really very simple. We first segment the sentences, then we make the tokenization process, that is to split the sentences in different tokens. Then we normalize the text, lowering casing it, removing stop words and some tokens that not give information for the classification process. And then we represent the raw text in the vector space by using a weighted vectors with TF, IDF weights. Here we have an example of some categories and the representation of the main words that represent different categories. For example, for computing category, we have PC, monitor, USB. The site is in Spanish, so maybe there are, if some of you does not read Spanish, there are some words that may not understand. In automobile category, we have, for example, different brands of cars, and these are the descriptions. So regarding classification techniques, we use decision trees, random forest, logistic regression, and support vector machines that are nowadays classic algorithms of machine learning. But we want to make a quick develop of this project because they were very eager to have the results. So we did not enter in another more sophisticated classification algorithms. So the first experiment we performed was to classify the dataset we have in these 28 level 1 categories. Here we did not group the items category that I will describe before. And we obtained very good results despite the simple classification algorithms that we choose and the simple natural language processing tasks. Then these are the results for a cross-validation process, and we select support vector machines with a linear kernel because it gives the better results in this experiment. Since the accuracy may be not very representative of the metric of the results, we also perform a holdout technique to evaluate by training the classifiers. In this case, the support vector machines classifier with 70% of the information available, and we use the other 30% for testing. We observe that we have very good results for most categories. For example, for the vehicles category, that is a level 1 category, we obtain 98% of precision, and 95% of precision and 98% of recall. And the worst category, that is coincides with the category that we have the lowest number of articles available, is services, in which we obtain 77% of precision and only 16% of recall. Then we thought in taking care of considering the information available in the hierarchical organization of the categories, and we built a multi-level classifier. So we train a main classifier with all the data set, in which we first decide which is the first category of the product ad. Then with all the ads for that category, we train different sub classifiers, each one specialized in one of the main categories. For example, a classifier for articles, a classifier for vehicles, classifier for properties, and a classifier for service. And the same we did in the third level of classification. So the first stage evaluation consisting in performing a stratified holdout with again 70% and 30%, 70% for training and 30% for testing, so that we were able to inspect the results for each level of classification. We can see here that the results obtained were really very good. We obtained 97 precision, 99, 99, and 89 for services that was the category with lower support. And analyzing some examples of wrongly classified products, we can see that even for a human, it was difficult to see if the category assigned by the user was the correct one. For example, here we have one title that is plastine, papel para hornear, papel. This is the text that we use to classify the ad. The real category was services, and the category that the algorithm predict was articles, which at first sight, it might be correct. So we think that the results maybe can be even higher. I'm running out of time, so I will quick up a bit. Here we have the results for second level classification. We can see that properties obtain almost a perfect classification, not the same for services, that was a bit lower. And here we have for vehicles and for items. You can see the full results in the paper if you like. And these are the third level evaluation. We can see that here we don't have vehicles because they don't have a third level category, but the results are really promising for the approach we perform. And the final evaluation consists in training a model with the whole data set and using new publications from the moment that we make the cut for performing the research. And the platform collect 6,000 new publications. So we pre-process the title of each publication. Yes, sorry.
1 minute left.
Okay. With the title and the first level category predicted with the first classifier, we select the second classifier. This second classifier, we also take as input the title, predict the second level category, and so on. And we have here the results. For level 1 category, we obtain 98% of accuracy. Here we can see some errors to see that maybe the wrongly classified instances may have a second chance. And here we have the level 2 classification. And level 3, we have to notice that for the level 2 classification, we are carrying over the errors of the previous classification phase. So at the end, the correctly predictions for all 3 levels was 76.34%. So to conclude, we take advantage of the hierarchical structure of categories to create a multi-level classifier. This make it easier the process of the sellers to selecting the categories appropriate for their ads when publishing a new article. It also make it easier for the portal administrations because they have only to check if the proposed category by the user corresponds to one of the proposed categories by the classifier. And we also hope to have improved the user experience when searching for products in some given category. As a future work, we want to explore a more advanced language models that are very common nowadays. And we also have the plans for predicting the category associated to the pictures that the users upload to describe the product that they offer. So we acknowledge Fundación Manuel Sadowski that give the financial support for this project, and I'm open to questions in this short time.
Thank you, Marcelo. We'll have time for just one question. So please, is there anyone in the room have any question? Speak now. So there's someone in the chat, Miguel. Thanks for your presentation. Have you tested the database with another machine learning as the neural networks?
Have you tested the database with another machine learning? No, we didn't. That is planned for future work. We have really short time to perform this project, so we use the classifiers that we know most, and we didn't try neural networks. The
Okay.
information also we have for each ad, the titles and the descriptions were very short, so I don't know if neural networks would give better results for this particular case.
Okay, thank you
Thank
very
you,
much,
Miguel.
Marcelo. And now we'll have our next speaker, which will be presenting the work and improvement in both machine algorithms using a dissimilarity measure in frequency domain transform. Is any one of the speakers of this work here in the room?
Yes, I'm here. Miguel de Jesús.
Thank you, Miguel. We'll try to cope with the schedule, so please, you have 10 minutes to start your presentation.
Okay, thank you so much. Ready, can you see my screen?
Yes.
Okay, thank you so much for your time, and thank you to the co-chairs for organizing this grateful event. So in order to present my work, an improvement in block matching algorithms using the similarity measure in frequency domains, well, the idea is to present firstly an agenda for today. And well, what is the idea to implement these algorithms? And as we know, in block matching algorithms, the idea is to find a local ways of patches or images in another big image. This could be implemented in real application, has video compression, image clustering, notch local reduction. And the idea is to use less compute calculations in comparison to the full search algorithms or certain search algorithms that can be very cost in terms of calculations. So in this work, we use certain techniques as hierarchical search in order to reduce these calculations. Well, there is too much state of the art articles in this phase. Well, there is four mainly areas where we focus to study this research. The first is the applications where we can implement these algorithms. The second is certain features that we can abstract to this, the test images. And of course, the machine learning approach in order to find these patterns inside of certain images. And the last, what kind of algorithms can be improved or could be implemented in this kind of research. So about in this general state of the work, there are related works that has been published, and this is more the most. This is one of the most important, where the number 3 is robust real-time phase detection with a complexity, computational complexity numbers of operation of OK and M, or multiplies the log of M. In this case, well, K is the search area, while N and M are the width and the length of the image, respectively. So this is the algorithm to get better improvements. The motivation of this work is, as I mentioned before, reduce the number of computation and calculation for these algorithms. So we know that implementing in video codecs, motion estimation, usually the algorithms use a lot of multiplies and sums. So this is important for battery saving if you are talking about certain smartphones. Image processing for video codec, that is another is essential application. And in this proposal, well, a part of reduce the number of operations, the idea is to implement certain techniques as the hierarchical search, with a difference in the first search that is certain to 5% of error. That is the idea to implement this algorithm. Well, this is the methodology, the general diagram to the proposal work. In this case, we make an environment to noisy certain image and select the dissimilarity measure. And this work is the Euclidean distance. After this, we implement certain low-pass filters or certain domains frequency transform, as you can see in the screen. But in this work, there are two main filters: is the Fourier filter and the Walsh-Hadamard transform. After this, well, we can prove these algorithms with certain techniques for finding these patches. These are the full search, hierarchical search, and after implementing the hierarchical cells in the previous domains or filter transform. And the last, we have a quantitative measurement to compare the performance of each algorithm. With the base of the pattern recognition, we talk along this presentation for a certain kind of images. In this case, well, this is the image to test, the picture extraction to understand how one image can be more texture than another, or if one image can be plain in terms of the pixels. So for this part, we implement also a data analysis to after the picture extraction and implement certain unsupervised algorithms for to achieve classify these three main texture, intermediate, and plain areas. Well, in general, talking about the dissimilarity measure between two image blocks, we realize full search algorithms. With one image with a noise environment, we need to find a patch inside of the original image. So as you know, NVIDIA Rio coded, there is too difficult to find these patches. So in this part, we use less computations, less calculations, and each dissimilarity measure is stored in some vector. This vector is sorted in the top of the button, the lowest dissimilarity, and the more similarity is under the top, the bottom of this vector. After sorter, we only can measure this performance in the first 8 blocks, because here we store the main dissimilarity. So we after this we can implement the Euclidean distance to find which is the best patch to match with the origin. That is the idea for all the methodology. Taking account these algorithms, you can, as you can see in your screen, this is a reduction of the numbers of calculations using the Fourier filter. In the second algorithm, using the discrete Walsh-Hadamard transform, instead of using all the picture until after the filter Fourier transform, we need to search in a radius area the size of these patches. So there are the two previous algorithms that I mentioned. And after that, there is a correlation. As I mentioned in the methodology, we need to understand what are the classes for these two images. In the first image for texture, for plain and intermediate. So we analyze information for each tested image. In this case, we have a correlation using the Kendall-Stone. We test in the article with Pearson also, but the most interesting correlation, it was for Kendall-Stone. For the next, after instead of using all the features, we make a reduced features using the reduced feature eliminations in order to have only a few features. The tested image was the name of these images, and the classes, we can see that the Cummings algorithm could have a separation between each image. So, for example, if we talk about the image of a bone, well, this is a texture image because they have pixels. There are some kinds confused by noisy images. In the time of aerials, houseboat, and bridge, there are so intermediate images. And from the left, the 4 last images are plain images. This means that it doesn't have pixels that can could be have so certain noisy, like a baboon image. Even we implement the principal component analysis, but using only two mainly components, we can't find a very long separation. So we need to implement 3 dimensions, 3 components for separate these classification for the images. So in these two best approach for unsupervised learning, the K-means was the better between these two. And the last, well, we need to see all the improvements, and we use this quantitative evaluation for performance all the algorithms, where we measure the cardinality between two finding blocks, where we have two lists. The first list contains all the original coordinates, and the second list contains the coordinates of the patches that were found for the algorithms. And we divide this for all the exhaustive full search. And well, this is escalate to the 0 to the 1, when 1 is the best performance and 0 is the worst performance. Well, for the results, we implement all these algorithms in the environment controlled using this specification. This was for grayscale image. This is the width of the length for the pixels, and we use the A-big palette for grayscale image. Consider the time. I don't put all the results for all the images, but I collocate all the essentials for this work. In these results, we can see that using these algorithms, we obtain better results in comparison with the full search algorithms, where in the axis Y, we can observe the performance of the algorithm finding that kind of patches. The axis X is the level of the noise that we implement in the images. As we know, the most we noise find it is so difficult to find that patches in for the algorithm. For baboon, it's the kind of texture image that we could see for the unsupervised learning. And certain algorithms using discrete cosine transform and the Walsh-Hadamard has better performance for this image in comparison to the plane. Well, as we mentioned before, the main idea of this work is reduce the number of operations, and as a result, you can observe that implementing this algorithm for search, we are using less calculations in comparison with the full search. Well, as a conclusions, we present two new algorithms for implemented hierarchical search in the frequency domain transform with less complexity, and we have a better performance dependent of the radius that we use to find these patches. In this case, we obtain the promised error. So this margin of accuracy was obtained for almost all the algorithms. And for the last, it should be noted that these algorithms, for example, using the adaptive cosine transform and the Walsh-Hadamard, has better results in noisy and texture images. And the future works for this research is develop and implement certain methodology that could be using quantum computing blocks. Well, this is a new technology. It could be interesting to implement this work. For a second one, this proposal could be implemented in a motion estimation real application. For the last, as we mentioned in the unsupervised learning, we can implement only one database that can help us to understand what are the kind of radius that we can implement for help these algorithms to find the best patch. And well, that is all for me. Thank you so much.
Thank you, Miguel. Does anyone in the room have any questions? Don't be shy. Okay, I don't think there is any question, but I find your work pretty interesting. About the future work, you mentioned the quantum blocks.
Oh, yeah.
Can you tell us a little bit more about it?
Oh, yes. Well, as we know, there are new technologies that we can implement. And as I have read, quantum block matching could help us to even reduce the kind of resources. As we know, 1 qubit could be storage 2 bits in 1 qubit. So if we use this quantum advantage, we can use the power of two resources. So this is insane talking about the storage of certain information, and it could be a future work for implementing this research.
Thank you very much. That is pretty interesting.
Mm-hmm.
Well, thank you, Miguel, and we'll continue with the next speaker, which gonna be presenting a speech recognition in digital videos without audio using convolutional neural networks. Is in the room any of the others? Carlos Avila?
Yes, I am Carlos Aviles.
Oh, thank you, Carlos. You can start sharing your presentation. And remember, you only have 10 minutes, so I will giving you the time when 3 minutes and 1 left, okay?
Can you see my presentation? Can you
Yes.
hear? No problem with the audio?
No, it is okay. Thank you. You
Okay.
can start now.
Good morning, everyone. I present our work titled Speech Recognition in Digital Video without audio using convolutional neural network. There are my co-workers. The contents, firstly, an introduction, proposal, results, and conclusions. What is the main idea of the work? Speech recognition with visual context, it's a technique that uses digital image processing to detect lip movement within the frames of the video to predict the word uttered by the speaker. A thought model with excellent results already exists. Most of them are focused on very controlled environment with few speaker interactions. In this work, a new implementation of the model based on convolutional neural network is proposed, taking into account image frame and 3 models of audio usage by means of spectrograms. The results obtained are very encouraging in the field of automatic speech recognition. Well, the proposal has 2 paths. From the video database, the first path is top frame segmentation, face detection, and the lips isolation. And the bottom path is only the audio. The audio has a transformation time to frequency in order to fit the convolutional neural network. And there is 2 databases, the database for the audio and the database for the video. The video taking into account only the lips moving, and then the classification is with the convolutional neural network, and finally the evaluation. But the database of video is a well-known grid corpus of audiovisual sentences from multiple speakers. The corpus consists of audio and video recordings in which the face is perfectly visible. The video resolution is 360 to 188 pixels, and the audio resolution is 50 kilohertz. The corpus contains 100 sentences uttered by each of the speakers. But the processing, the the main task is to take the leaps easily. So starting from the video, firstly, a frame is extracted. Remember, each second has 30 frames. So we have to take a frame and then develop an algorithm to detect the face in order to get the face detection. And after, with the face frame, we have to find the lips, only the lips area, and to get them in order to have a sequence of movement corresponding for each word. So there are many words in English. And for example, in the line A, we have the speaker, and the line B is the face detection, and the line C is the lips movement. So we have now the database for fit the convolutional neural network. And the other way, we have the audio. And from the audio, we propose 3 possibilities. One possibility is taking the full word in a single spectrogram. We apply a time frequency transformation in order to get an image of the word. So, and after the spectrogram type 2, the number of spectrograms is aligned to the same number of video frames. It means if we have 30 frames, we have 30 spectrograms. So we have more information. Of course, there are overlapping between spectrograms. And the number 3 type, the proposed type, the proposed structure, we had defined 10 equally divisions for each word. So we have 10 spectrograms for each part of the division. The division is equally spaced intervals. So with proposal, the proposal has 3 different use of audio. And the convolutional neural network is comprised of, convolution and polling, convolution and polling, convolution and polling, and convolution and polling for the video from the lips. And there is the number of the filters and the size at each level for the convolution. So there are 4 feature extraction tasks for the video. And there are a flattening layer and a groove neural network in order to classify. So we define 2 tasks for the one for the video, the top, and other parallelly for the audio. And the audio is the representation by spectrograms. So the spectrum is defined 64 by 64 in RGB. So we have the convolution, polling, convolution, polling. And now for the audio, we have only 3 feature extraction tasks. 1 here, 1 here, and 1 here. And after a flattening in order to get a vector. After that, both information, video and audio are merged in a single vector to develop the classification. So the classification is each word. And the entropy of the function for the Young loss in formulate as this formula. And the total loss function is structured like this with the probability function, probability density function for audio, for video, and for classification. So there are three main tasks for the loss function. And CE is the word for audio, the word for video, and for classification. As a result evaluation, there are 3 time spectrograms for audio. So we have three evaluations for training and for validation. So there is the result for type 1, for type 2, and for type 3. And there is the number average for training and validation. So for training, the accuracy for the spectrogram type 1, 85, for the second 78, and 94 for 3. So the mean average is 85. And comparing for the state of the art, comparison for the most competitive world, there are different words. The database is the same, the grid corpus, the pre-processing, almost finding the lips, all the guys, and taking the audio, and the deep learning model for each of the authors, and for us, 2 parallel convolutional neural network plus growth layer. And you can see the improvement for the classification, the accuracy, from 47 to 85. So we have an improvement from 3%. As a conclusion, yes. Oh, I think that it's a question, but as a conclusion, the processed deep learning model was successfully analyzed and programmed. The 3-time frequency representation for the audio is corresponding to 3 kinds of spectrograms. Spectrogram per word, spectrogram per frame, and 10 spectrograms per second were evaluated. A single frame from the transformer audio shows the best performance with good accuracy in both the training and validation set. So thank you very much. And do you have any questions?
Thank you, Carlos. Does anyone in the room have any question? Here in the chat, we have one question. It's from Miguel. It says, very interesting work. What kind of domain transport do you implemented for the voice?
For the what? Here.
I think it's voice. Voices?
Or words.
A speech of voice.
For the words, we take the corpus, the benchmark, use it for the different authors, for the different audience. So there are indications, there are limits for each word, and for the characteristic, for the number of words, the time of pronunciation. Every features are in the corpus. So we have the corpus as it, and we use for the audio from the video.
I have one more question, and it's about your results. You are presenting the 85% of accuracy. I understand the 85 is the one that you obtained during the training phase, right?
Right.
Okay, so are the results in this table are also reporting the training phase or the validation phase?
Yeah, in order to compare with the most competitive words, the most competitive reports the accuracy in training.
Okay,
So in order to compare, we have the same comparison, the same value, the same result. But of course, there are other results, very important results like validation. But in this work is for comparing to the state of the art, the training accuracy.
okay, thank you very much.
Thank you very much to everyone.
Another question, so let's continue with the next speaker. We'll be presenting TrumpetNet, a convolutional neural network with self-attention mechanisms for visual detection of trumpet figuring. Hello, Dr. Valdez. You have 10 minutes. I will let you know when you have 3 and 1 minute left.
Okay, thank you so much. I'm going to share my screen. Okay. Good morning, everyone. I'm going to present my my work. It's called TrumpetNet, a convolutional neural network with self-attention mechanisms for visual detection of trumpet fingering. Here in this slide, you can see my team. The content of this presentation is the introduction, the state of the art, the proposal, some results, the conclusions, and the future work. Okay, as an introduction, here in this work, we are focusing on wind instrument, especially on the trumpet, because in a future work, we plan to create an autonomous teacher for also teaching this instrument using both audio and images. So as first step, we declare the problem as the detection of the position of the bulbs of the instrument. So in a first stage, we planned to mount a camera in front of the trumpet in order to detect the positions of the bulbs. Why it is important to detect this position? Because audio is not the only source to detect an error or a mistake during the interpretation of a song or any music. So we focus on also using visual information. So that's why we decided to use a convolutional neural network, because we found that this algorithm is a good way to start the classification of these visual cues. So the state of the art is not as much as we expected, because most of the previous work or most of the state of the art focus on another instruments. So here in this slide, you can see that most of them are focused on guitar, piano, and also flute. So the first work is focused on guitar. They use video classification. They use all the frames of the video and use image processing techniques to segment the fingers of the player, and then use traditional algorithms such as support vector machines and all logistic regression to perform the classification of these cues. The second work is focused on trumpet, but they use audio. They use support vector machines to classify these audio cues and use feature restriction techniques to perform this classification. The third work from Han they use audio classification, but focus on the flute. And finally, the work from Joseph it was released this year. They focus on the piano. They use a keep-on detection technique to extract the fingers from the images and use a gun to estimate the note. So as you can see, most of the works focus on other instruments, and the only one that focuses on trumpet uses audio. So this was a big small problem because we did not find any other data set to work with the trumpet. Also, we did not found any other data set using images, only audio. So the general goal of this work is to identify the trumpet piston positions through images using convolutional neural networks. So our proposal is the following. We will have a data set from new students. We are going to use a CNN to estimate the position of the bulbs. So this is our proposal first approach to classify these images. For this, we created our own data set. It's called SIG Trumpet Detection Dataset. You can find it on the link below. It's on GitHub. So this data set includes 188 images with 183 images for training and 55 for testing. These images are taken from beginner students. So we took these images from all the positions on the trumpet. Essentially, we have 8 positions on the trumpet. You can see them on the screen. These were all the positions on the trumpet, and this was our data set. The labels are from 0 to 7 to select one of those positions. So we use 2 CNN architectures. The first one is called TrumpetNet. It is based on ImageNet and AlexNet convolutional neural network. We use RGB images, each one of the positions of the trumpet, of the piston of the trumpet. So we use RGB images followed by a first feature extraction stage in which we extract all the features that contains that single image. And then we use a classification stage. We use 2 fully connected layers to perform this classification. And the output are only 8 neurons, in which each one of the neurons will tell us about the position of the trumpet, of the piston of the trumpet. So this was our first architectures, but we found that this neural network focused on all the system of the bulbs, so it does not focus only on the piston or the bulbs. So we decided to use self-attention mechanisms based on the paper that we show in this slide. So these self-attention mechanisms is implemented as follows. We use 2 parallel convolutional layers from using a 1-by-1 kernel. We add these two convolutional layers. Then we apply ReLU as activation function. Then we apply another convolution using a 1-by-1 kernel, followed by a sigmoid activation function. And then we multiply these results from using the original image, and we obtain the output of this self-attention mechanism. So our architecture with self-attention mechanism is presented in this slide. We added the self-attention mechanism next to a convolutional layer. We selected this architecture, we selected to use this self-attention mechanism in the convolutional layers because they are the ones that extract all the features on the image. So we use this mechanism to put attention on the valves or pistons to perform a correct classification. So the classification stage is the same. We use two fully connected layers and 8 neurons at the output. So the results, we have quantitative results. So in this table, you can see the results of this neural network architecture. In the first column, you can see the trumpet net. We use accuracy, precision recall, and F1 metrics to evaluate the performance of this neural network. But we found that it was not enough, or this architecture did not work with the original dataset. So we decided to use data augmentation techniques. These data augmentation techniques are random rotations, random brightness adding, or we use random rotations, random adding. We did not use flipping because it will change our problem, because we are only focusing on right-handed players. So if we change for left players, this will change our problem. So we need to perform another experiments with left-handed players. On the third column, you can see the trumpet net without augmentation. Sorry, on the third column is with a self-attention mechanism, but without data augmentation. So we can see that also the data set is a small data set. So that's why we decided to use data augmentation techniques. And on the last column, you can see the full trumpet net with self-attention mechanisms and with data augmentation. So you can see that the results are really improved using both techniques, using the self-attention mechanism and data augmentation. So in this slide, you can see the qualitative results. So in column A, you can see the results of the trumpet net without data augmentation, the original trumpet net. You can see that it's not, we use the GradCam algorithm to see where the convolutional neural network is focusing its attention. So in the first column, you can see that it's focusing on the fingers, and the fingers is about it's a bad way to focus or to classify this position, because we have two similar positions, that it's 0 and 7, because we have the 3 fingers at the same level. Also, if we move the camera, we can change the we can change the problem and classify it, and obtain bad classification results. On column B, you can see the GradCam algorithm with data augmentation. You can see that it's focusing on all the image, and it's not working as well as we expected. On column C, you can observe that it's focusing on the bulbs, but because we don't have so much variations on the data set, we do not obtain good results. And finally, on the last column, you can see the GradCam on the trumpeted model with self-attention mechanism and data augmentation. So you can observe in yellow that it's focusing now in the bulbs and not in the fingers. Also, you have the confusion matrix. On the left, you have without data augmentation, and on the right, you have with data augmentation. Also, with attention, you can see on the right and the left that is not classifying as well as we expected, but on the right, you can see that we almost classify all the images. So the conclusion of this work is that we presented a visual data set for keystroke detection applied to the trumpet. in which we can detect the action exerted on the instrument bulbs. So also it was demonstrated that it's possible to classify these images using a convolutional neural network model. And furthermore, it was shown that data augmentation techniques can improve the model's performance by introducing variations on the data set. And finally, we showed that self-attention mechanisms improve the detection of the bulbs on the trumpet. As future work, we propose the following task: so employ different CNN models to vary hyperparameters and enhance classification. Additionally, we propose use different perspectives of the instrument's performance, such as top-down view or a side-angular view, to adapt the model to various viewpoints. Also, to conduct experiments with left-handed performance, allowing us to adapt the model to analyze their execution as well. And finally, use both audio and images to classify the musical notes on the trumpet. So thanks for your attention.
Thank you, Dr. Valdez. Does anyone in the room have any questions? Well, I have one question. And which kind of data augmentation techniques did you use for this work?
Okay, we use random dot rotations from 0 to 30 degrees to change the angle of the performer. We also use a brightness change with a percent of from 0 to 20 randomly. And we did not use flipping because it changes the problem, as if we can see it a left-handed player. So that's why we did not use flipping. And that's all. From the original 188 images, we grew the data set to 4,700 images.
Okay. Thank you very much.
Thank you so much.
So the next speaker presenting today will talk about where convolutional neural networks approximate the phylogenetic of human populations with face images. This work is presented by Fernando Aguilar. Is Fer here?
Yes, yes, Elsie, can you hear me?
Yeah, I can hear you. Kind of low, I can hear you.
Okay, all right, thank you. Can I share a screen?
Yes, sure. Remember, you have 10 minutes and 5 for questions.
Okay, all right. Can you see my slides?
Yes. Remember, I will doing this when you have 1 minute left, okay?
All right, thank you, Elsie. Hi, everyone. My name is Fernando Aguilar Canto. I'm here with my co-authors, Juan Eduardo Luján García, Alberto Espinosa Juárez, and Dr. Iram Calvo. We are going to present this research paper entitled as Can Convolutional Neural Networks Approximate the Phylogenetic Tree of Human Population with Face Images? So we're starting with a bit polemic question, and we would like to answer this. Here, first of all, phylogenetic analysis is usually performed by using genetic sequences. But sometimes the genetic sequences are not available, so the experts might require other phenotypic features to infer the phylogenetic traits, and that's the case that we would like to study. In the case of when we only have images, can we approximate the phylogenetic tree? That's the main question. And as most of you might know, the state-of-the-art of vision-related tasks are comprised two kinds of neural networks. The first of them is the convolutional neural networks and vision transformers. In the case of CONVNETs or convolutional neural networks, we're going to use them because there are some of them available and pre-trained with images of faces, and that's the main reason why we are using CONVNETs. So let's continue. And there are only two works that I've found that are most related with this presentation. The first of them is the work of Kiel, which use CONVNETs to classify images. and then you use the error to create a distance matrix, and that matrix was used to generate the tree by using hierarchical clustering. Another approach was performed by Hahn and Peterson, that they extract features with the convolutional neural networks and then use Bayesian inference to construct the phylogenetic tree. And the approach that I would like to present is a bit similar, maybe a combination of the previous two. We have a image encoder, which receive an image, a particular face of a person, and produce embeddings. And we have lots of embeddings of different persons. And finally, we can perform hierarchical clustering to induce the phylogenetic tree. And finally, we can compare the phylogenetic tree with the trees that were constructed by the scholars previously with different methods. There is no consensus about how the human population has evolved. Actually, there are three proposals that we are going to compare with. We don't want to enter into discussion because this discussion requires several kinds of data that we are not using in this case. And most of them rely on genetic sequences. So we are not going to discuss which one is correct. We are only using that those trees to compare with our proposals to see how similar or how dissimilar are the trees that are generated with only images. So in the case of data acquisition process, we perform word scraping and use some pre-processing techniques. In this case, we are using the face recognition module to select and crop the region of interest in the case of the faces. And finally, we select the classes that have at least 10 images to avoid any problems with that. And finally, we got 30 ethnic classes with 419 images. And we also exclude some groups manually because when we are dealing with word scraping, there is a problem. For example, if you search for the word she, you might not find what we would like to find, and that's the preposition that we perform. Finally, the visual encoders that we use are three. There is the BGG16, ResNet 50, and the face recognition module, which didn't explicitly show the architecture in this, but it's a very good model. And the three models were pre-trained with faces, with image of faces, and that's a very particular requirement that we are looking for because we only have to do transfer learning in this case, and that's the reason why we are using these kind of encoders. There are two main subtasks, for example, for the ethnic classification. We're not pretty interested in that, and we won't be focusing in that. What we are interested in is the generation of the tree by using hierarchical clustering with three different algorithms. The first two of them, OPMA and neighbor-journey, are pretty useful in biology. And the last one, hierarchical agglomerative clustering, is most commonly used in computational context. So the first two of them might be the best ones, but let's see how them perform. As metrics, we have the first four of them are distances. They compare the distance between trees, and in this case, we would like to minimize these distances. And the last two of them are measure similarity, and in that particular case, we would like to maximize them But it's important to note that we are not performing any optimization scheme or any optimization algorithm. We are just using these metrics as metrics itself, so to compare our results with the ground truth. And as results in the subtask A, we didn't see a very good result. That's probably because we don't have enough data. We might see better results if we provide much more data in this case. But as I previously mentioned, we are not too interested in this subtask. We are more interested in the subtask B, in the tree generation process. And as you can see in here, different dimensions of comparisons, because we have in one hand, sorry, the visual encoder that we're using, in this case, BGE16. And on the other hand, we have the algorithm that produce the hierarchical clustering process. In this case, we have three algorithms, and we need to compare these three trees with the three models that we presented previously. And in this case, we can compare all of them, and we can see that the better results were achieved by the ResNet 50 with the OPMA algorithm. It produces the best metrics of in general. So we believe that that was the best tree that was generated. Here you can see the tree that was generated with our best model. In this case, we can see pretty consistent results, except for some outliers. For example, the Australian group is not well classified, but the other ones have some consistency. If we can see in this distant metrics to see how each group compares each other. Finally, we can see here the difference between the Grand Tour, the Model A, which is on the left, and in the right, you can see the tree that was generated by our process. Finally, as conclusions, I think that generally this method produces consistent results, but there are some ethnic groups, for example, the Australian ethnic group, but that was not well classified. But in closely related groups, we observed pretty good results. But there are some challenges to deal with convergent evolution. But that's something that we need to deal when we are facing with using only phenotype. The best results were achieved with ResNet 50 and the face recognition model, especially by using OPNA algorithm. Finally, we can conclude that while face embeddings can capture some similarities, they have limitations because evolution is complex. So we might rely more in using genetic sequences when it's available. But we can see that when we don't have any other kind of information, we can use images and produce pretty consistent outputs. And that's the end of my presentation. Thank you very much for your attendance.
Thank you, Fer. Does anyone in the room have any questions? Eduardo, you can talk.
Yes, doctor. What other type characters could be used to improve results. And when we are dealing with phenotype, usually the biologists use measurements of, for example, if they are using fossil record, they measure some metrics to create a feature vector, and they compare with by using the hierarchical clustering process. And that's we can, in this case, we are not using measurements, and we're using only the images, but I expect that it would be we can use convolutional neural networks instead of measure some biological constraints in the fossil, for example. And we, in addition, if we are dealing with human populations, we can use other multimodal aspects. For example, we can use language, which is in this case, language might provide a different tree, because the languages are organized differently. But there is a discussion that indicates that maybe the human evolution correlates with with language evolution. So it might be acceptable to study in this case language, which might be part of the phenotype. However, we need to understand that language and human evolution might be slightly different. So that's another approach that we like to study in the future.
Thank you very much.
Thank you.
And we'll continue with our last speaker for this block. So he'll be presenting the associative pattern classifier progress in theoretical understanding. Is in the room any of the speakers for this work? Okay, here is Sergio Valadez. Can you try to speak? Because I cannot listen to you. Can you check your microphone, please? Okay, we'll wait.
Can you hear me?
Yes, you do. Thank you.
Yes, sorry. I
you
have technical problems.
Okay.
Yes.
I will let you know when you have 1 minute left by raising my hand like this. So don't think it is a question, it's just that you have 1 minute left, okay?
Okay.
Thank you. You can start now.
Let's begin. Can you see the presentation?
Yeah.
Okay. Well, I am Sergio Valadez. I am a full-time professor in the software engineering program at the Universidad Politécnica de Pénjamo in Guanajuato, Mexico. I will present the associative pattern classifier in the sense of progress in theoretical understanding. Well, as an introduction, the associative pattern classifier, or APC for abbreviation, is an associative memory, or AM, with a specific purpose of pattern classification. This algorithm is based on the training rule of the linear associator or ELA, and the recovery rule of the Lerner matrix associative memory. This algorithm enables real number operations, overcoming the limitation of the Lerner matrix, which operates exclusively on binary numbers, and also removes the orthogonality constraint of the training in the linear associator. Until now, since 2003, there has been a lack of clear information that will allow us to elucidate how it works. However, it has been deduced that it is accurate, as evidenced by the fact that some students have been developed, such that reference in the screen. This paper aims to give, or the objective is to give a theoretical understanding of this algorithm for future improvements. How this algorithm works? At first, we need to define some notations, in particular, the fundamental set of associations, such as S equals to X power to the K and Y power to the of the K, for K equals to 1 to 2P, where where X to the K power in real numbers. We're representing the set of input patterns, and Y in 0 and 2 set, representing the set of output patterns. Here, N is the dimension of the vector X, Q is the dimension of vector Y, and P is the cardinality of the fundamental set. The class seed in 1, 2, 3, 2Q, to which each input pattern X belongs is defined by the equation number 2, where Y subscript J represent the class index. The first phase is the learning phase, where a translation vector is calculated. Subsequently, after the translation of all patterns X in the fundamental set is carried out by the equation number 4, which is a difference between two vectors. The matrix M is computed by equation 5, where it's a dot product. And the last phase is the recovery phase, where an input pattern, a noisy pattern could be, is initially translated with respect to the translator vector X bar, and the following step is a dot product between matrix M, which is the memory of the associative pattern classifier, multiplied by the vector X. And the class vector Y is obtained by equation 8. And the class index is that belongs to the position J in the vector Y power to the W. Let's try an example For example, we have here 3 vectors. Each one belongs to one class, where P is equals 3, N equals 2, and Q equals 3. The vectors can be illustrated in this picture in a Euclidean plane, where we have the 3 vectors X and the translator pattern X bar. The input patterns were translated by means of the equation number 11, and the matrix M was constructed by equation as in the equation 12. We can see here the memory, which is this one. And from this matrix or memory, we can extract 3 vectors from the matrix, 3 row vectors in this way. And we can see these vectors in figure number 2. In this plane, we call this plane a translation plane. And in this translation plane, this is a translation plane because we translated the 3 vectors by using the translator vector. And in this plane, we can see a system of concurrent vectors. This system is constructed by sketching a line between the vectors or points in the plane, the vectors M superscript 1, M superscript 2, and M superscript 3. And we calculated a series of perpendicular lines to these lines, and we can see in figure 4 the regions and the linear decision functions or planes of the associative pattern classifier in the original plane. This region was calculated by using the translator vector forward to visualize the regions formed by this algorithm. We established a theorem 1, to determine if the system is a static of concurrent vectors following the Newton law, where the sum of the forces equals 0. We can insert equation 3 into equation 4, and we have equation 52, which is a simple replacement. And when we developed equation 52 to the translated patterns X in the fundamental set, we obtain the following expressions as in equation 53. And from this equation, we can extend equation 5, and it becomes as in equation 54. And if we assume that each vector X is associated to a distinct class, Y, we can define Q equals P classes. Thus, we can define equation the question 56 as a matrix where each row is a vector, and without loss of generality, we can sum all of these vectors. And when we sum these vectors, we obtain a sum that is equals to 0, which is the value when we sum all row vectors of the matrix. That means the associative pattern classifier is a system of concurrent vectors in static equilibrium, which means that the algorithm cannot could be not adjust because the system is in static state. We have an experimental protocol. We constructed two artificial databases. The first one is you can see the distribution of these patterns in figure number 6. These patterns are not overlapping. And the second one is in figure 7. These patterns present an overlapping. The results, we compared our algorithm of the associative pattern classifier IPC to another algorithms of the state of the art, such as minimal distance classifier and naive Bayes, artificial neural networks, super vector machines, 1NN, or C4.5, which is a decision tree. As you can see, for the first database, we obtained a 100% classification because the patterns are in a balanced distribution. Here are not overlapping patterns. And in the second one, we obtained 83% of correct classification, which is similar to the super vector machines. However, we have in this database overlapping patterns. With these experimental results, we showed that the algorithm function in the way we demonstrate with the theorem, in the sense that the algorithm construct an static system. As a conclusions, the row comprising the memory are concurrent vectors transform a system in equilibrium, allowing the algorithm to distribute the patterns in a balanced way. Well, the APC achieve a proper separation of a set. The pattern cannot achieve an absolute separation because there are a neutral region in the algorithm. The algorithm generates a generalized nonlinear function, enabling the APC to be efficient and sweet in separating a set of evenly distributed classes. As a future work, we recommend to explore methods for eliminating the neutral region and to employ the Hoffman memory in the recovery rule. The Hoffman memory is another associative memory, which is a dynamical system in contrast to the statistical system that the APC forms. Additionally, finally, we recommend to use heuristic optimization algorithms to determine a better pattern translation. We have here the reference, and thank you for listening.
Thank you, Sergio. Does anyone in the room have any question? Okay, I think there are no questions, so we'll take these 5 minutes as a break since we are starting the second block. At 12:30, please be on time, and we'll continue in 5 minutes. Okay?
Thank you.
Thank you, Elsie.
Buenas tardes, solo para probar el audio, si alguien puede comentarme si me escucha.
Hola, doctor. Sí, sí se escucha.
Ok, gracias. En 3
Doctor
minutos
Freddy,
comenzamos.
yo lo voy a estar apoyando para dejar entrar a las demás personas en lo que usted dirige la sesión.
Te agradezco mucho. Tú me dices si comenzamos a la hora exacta o esperamos unos minutos.
Déjeme ver quién va a empezar rápido para ver si ya está en la sesión. Ah, no, todavía no llega. Creo que esperar un par de minutos más.
Sí, claro, yo aquí estoy. Saludos. Hi, everybody. Please, we're going to change the sound. Tell me if someone is listening to me. ¿Alguien me escucha?
Sí, doctor, sí se escucha bien.
Yes.
Ok, la indicación es que la sesión se va a hacer en inglés, entonces porfa le voy a pedir que vamos a tratar de respetar. He estado en otras sesiones y todo se está haciendo en inglés. We're going to begin with the first presentation with the paper cyclic generated pneumonia chest X-ray image evaluation with vision transformer, with the authors Gerardo Lugo, Eduardo Valdés, Diego Peralta, e Irán Cabo. You have 3 minutes. Next, when you finish the presentation, we have 5 minutes for question. You can begin.
Es que presentación. Bueno, ¿se me escucha?
Sí.
Yes.
¿Pueden ver la pantalla compartida?
Yes, we can the window. We can the window.
Thank you. Good afternoon, everyone. My name is Gerardo Lugo Torres, and today I'm going to present the work titled Cycle GAN Generated Pneumonia Chest X-ray Image Evaluation with a Vision Transformer. The overall structure of the present talk consists of presenting, first of all, the talk objectives, a short introduction of the work, the methodology used in the work, the presentation of the work results, and finally, the conclusions. First of all, the central idea of the work can be summarized in the question: do the performance metric of freshet inception distance, FID, and inception score in the cycle GAN model are adequate to determine how real a generated chest X-ray pneumonia image is? In this study, a cycle GAN model was employed to produce artificial images depicting 3 classes of pneumonia images. One class was general pneumonia, the second class was bacterial pneumonia, and a third class of viral pneumonia. The quality of the images were evaluated assessing and contrasting 3 criteria. The first criteria was performance metric of the cycle GAN model with FID and ES score. The second criteria was clinical assessment of 3 respiratory experts with the application of surveys. And the third criteria was the results of classification of a visual transformer. And the overall results showed that the evaluation metrics of the cycle GAN are insufficient to establish realism in generated medical images, at least for chest X-ray generated pneumonia images. First, an introduction. What is image-to-image translation? Image-to-image translation is a computer vision technique that involves the transformation of an input image from one domain into an input image into another domain. While this is important, preserving important thematic information. This technique has various applications, including style transfer, like in these pictures, or super resolution, colorization, and more. Like I say, some interesting examples are shown in the current image, where you can transfer style like from a horse. You can make it have a stripe.
Sorry to interrupt you, but we cannot see your presentation.
No?
No, it's only showing the contents slide.
A ver. Wait a minute. A ver. Dejar de escape. Wait a minute. Es dejar de compartir. A ver. Compartir pantalla. Pantalla completa. Permitir. And this one. You can see it. Objective.
It's loading the screen.
You can see it?
No, try again, please.
Voy a dejar de compartir. Ay. Compartir pantalla. Pantalla completa. Permitir. You can see my screen?
No, Gerardo, you can share
Oh.
only the screen of the presentation.
A ver. Wondershare es esta de acá. Permitir. You can see the screen?
No.
I think you need to get authorization because in that case the people is directing this conference must give you authorization. I think I don't know exactly, but
I have request.
Try again to share it like you did at first, please.
Yes, is permitir. You can see it?
yes.
We can see.
Yes.
If I make these changes, can you see it? The changes? Well,
yes, we can see it.
Sorry by these delays. Like I was saying, this is what I was meaning to tell you about the image-to-image translation. The image-to-image translation just transforms an input image from one visual domain to another while preserving its semantic content. These are some interesting applications that can be used for image-to-image translation. You can transfer style from satellite to map or MRI to CT scans or vice versa. Now, for the methodology used in this work for the image-to-image translation, in this case for generating chest X-ray pneumonia images from normal chest X-ray, we use what is called a cycle GAN model. In our case, like I say, we generate synthetic chest X-ray pneumonia images with the use of the dataset label optical coherence tomography and chest X-ray images for classification. The images were divided into 3 files: 1,341 normal X-ray images, 2,531 bacterial pneumonia images, and 1,345 viral pneumonia images. For the images to work with our cycle GAN model, we use we resize the images to 256 by 256 pixels. In this image, you can see some of the examples of the user dataset of pneumonia chest X-ray images, it being a general pneumonia, bacterial pneumonia, and a viral pneumonia image. First of all, well, this is the architecture of the cycle GAN model we use. It's a 200 by 56 by 256 by 256 pixel architecture. First of all, a generative adversarial network, or GAN for short, is a type of deep learning model consisting of two neural networks, a generator network and a discriminator network. The overall, or the summary of this, is that the generator tries to produce data that is increasingly difficult for the discriminator to distinguish from real data, while the job of the discriminator aims to become better at correctly classifying real and fake data. The training of a GAN involves a two-player minimax game between the generator and the discriminator. And now for the cycle GAN model, that it's a type of GAN model, a cycle consistent generative adversarial network, is designed for unpaired image-to-image translation, what we are supposed to do with the chest pneumonia images. And first of all, or in a summary, is that the key idea behind cycle GAN is to enforce cycle consistency during training, which helps maintain the content and style of the original images. These generators learn to transform images from one domain to another. And there are also two discriminator networks, one for domain A and one for domain B. The cycle count generator in this model is composed of 3 distinct components, namely an encoder, this part, an encoder, a transformer, and a decoder. And finally, a patch count for the discriminator to distinguish between real and fake images. The other one model we use for assessing or classifying the images was a visual transformer. A visual transformer, in short, is a neural network architecture that applies the transformer architecture that is mostly used in natural language processing task to computer vision task. In this case, was adapted, and the key components as a visual transformer is that it has a self-attention mechanism, a multi-head attention mechanism, and a positional encoding, and some have a stacked transformer layers for refining the features extracted from the input data. The evaluation metric for our proposed method or our proposed model was using a Frechet inception distance and an inception score that measures the quality of the generated images. A Frechet inception distance, in overall, it's if the score of the Frechet inception distance is lower, is better, and for the inception score, higher is better. Now for the results, is the important part of this work, is these are some images of the generated images, synthetic generated images of our cycle GAN model. For the cycle GAN training, we trained for 100 epochs for a total of 1,341 synthetic images generated of three classes. General pneumonia, that is in the subclass B, the bacterial pneumonia class, and viral pneumonia class is in this in the subset D. For each set of generated images, the quality of the generated images along the 100 epoch training was assessed at the epoch training of these intervals: 25, 50, 75, and 100 epochs. For each set of generated images, its corresponding feed and IS values were calculated. In this table, we summarize the better performing epochs for our generated images. For general pneumonia images, the better performance was obtained at 25 epochs with a feed score of 64. For the bacterial pneumonia, we obtained the better results with 50 epochs of training with an overall result of 64.53. And for the viral pneumonia, which has the better performance of overall with respect with these metrics, we obtained the better results at 25 epochs of training. Now, these results, we contrast them with the expert evaluation. We give these images in a survey to 3 experts and get their assessment if they think that the images were false or were synthetic, and if they think that they were general pneumonia, bacterial pneumonia, or viral pneumonia. From this, we get these results of the survey expressed by the assessment of 3 respiratory experts. And this is contrasting with the performance of the feed and IS score. In this summary, we get that the general pneumonia dataset, by the assessment of the expert, obtained the better results at 25 epochs, overall with the 3 experts. By the bacterial pneumonia at the 75 epochs of training, they achieved to full in a high probability of almost all the 3 experts. And the viral pneumonia performed rather poorly, which is contrasting with the overall performance of the feed score, which was the better of the 3 datasets. And then we contrast this with a bit the classification model that was trained purposely with specifically for the discrimination between pneumonia images and normal chest X-ray images. This table just classifies, so it's a basal score of the capability of the bit model used for discriminating real images. This is with almost with 97%, they discriminate correctly pneumonia, bacterial, and viral pneumonia images and normal images. These are real images. And for this, we input the synthetic generated images, and we were able to get the best performing data set of generated images with the bit classification were obtained at with 50 epochs of training. 95% of the 1,300 images generated were classified as pneumonia. In the case of the dataset of synthetic generated bacterial pneumonia at 75 epochs, 95% of the 1,000 images, 1,371 images were correctly classified as pneumonia. And for the viral pneumonia, they performed rather poorly. They were not able to really fool the VIT transformer into classifying correctly. They only performed like 67%, almost like how do you say, como un volado. Yes, and the conclusion of this work is that the results obtained, you can see that the feed and inception score values associated with the quality of the generated image are insufficient to determine how realistic the generated chest X-ray pneumonia images were. And this gives us the question that this needed a better assessment metric that would allow the use of generated images more reliably, preferably in a research clinical environment. And this is all for me. Thank you for your attention. I am waiting for your questions, if you have any.
Thank you so much, Gerardo. Somebody have a question?
Yes.
Somebody have a question? Okay, I have a question, Gerardo. Do you have contact with a physician, with a doctor, in this work? Is work is interesting with focus, with computational focus, but it's necessary also coin with the vision of the expert. In this case, do you have contact with a doctor or with a physician, Gerardo?
It was with clinical physicians that daily clinical experts that work in the respiratory healthcare unit of the two Institute of Health. One was the National Institute of Respiratory Disease, INER, and another expert was from, two experts from INER, and another expert that assessed the quality of the images was from the Institute of National Cardiology, Institute of National Cardiology, and they were experts in the assessment of only chest X-ray images. For this work, we also proposed for future works, also assessing a more specialized type of experts like radiology, that are experts that obviously all they do is check chest X-ray images. But that's for future works, no?
Yes, it's important to consider for a future work. Thank you very much, Gerardo. We're going to continue with the next presentation. Robust image registration for analysis of multi-source is fundus image. For the authors are Edgar Lopez, Edgardo Felipe, Eduardo Valdez, and Iran Calvo. You can begin. You have 10 minutes for presentation and 5 minutes for question.
Thank you very much. Please, I am going to share my screen now. I think, are you looking my screen? Please, I am questioning.
Yes, Dr. Edgardo. You can see.
Yes, we can see the screen.
Fine. Then I can begin with my presentation. Good afternoon for the auditorium. I am going to explain you our paper with the name Robust Image Registration for Analysis of Multi-Source eye fundus images. I am from Computer Research Center. Image registration consists of the combination of information contained in two or more images in such a way that the resultant image will contain a richer set of data from the image that are combined. That means that if we are working with images, retina images, the name, they are fundus, eye fundus images, and some situation presented with our expertise is that it is impossible to see some information when we capture the images. For that reason, this image registration is presented. Image registration is essentially a task that requires combining information present in several data sources, such as image fusion, multi-channel image restoration, and so on. There are two main types of image registration techniques, based on area and based on image characteristics. In our case, we will base ourselves on the characteristics of the images. This paper was created for the detection of microaneurysm in color optical fundus images. What are microaneurysm? Microaneurysm are present in images, in general, images, ear images, is presented as tiny drops of blood that appear at the ends of venules and asteroids, visible on colored retinal images, which are the first symptom of diabetic retinopathy. Detection of micro aneurysm in optical fundus images can be challenging, especially during the early stage of diabetic retinopathy, as they are too small to be observed. I am going to show this now. In our study, we focus on the registration of two types of retinal images: optical images in color and fluorescein angiography images in gray levels. To obtain the fluorescein angiographic image, the doctor injects a small amount of sodium fluorescein into the patient, making the blood opaque and making the detection of microaneurysm easier. These appear as small bright spots. This is presented. This is the original optical color image. Here are present the microaneurysm, but they are not visible. Maybe we can see here in this part something, but they are not microaneurysm. They are hard exudates. It is another problem. In that case, this image in grayscale, we can get here, it's possible to see a little better this information of hard exudate, but microaneurysms are not visible. In here, it's presented a fluorescent image. Here you can see the microaneurysm. These are the microaneurysm. little bright dots are the microaneurysm. It is the first symptom of diabetic retinopathy. These retinopathy are present here also, but they are not visible. And it is very important to know that if the optical image presents a microaneurysm, for that reason, it is necessary to register the optical image and this fluorescent image. Here it is better visible. Microaneurysm, you can see them, and here it is not possible to see them. They are there, but it is not possible to see them. Our registration process consists of 5 stages. In general, well, one preprocessing stage of the image to be registered, and the registration stage using the SIFT, Scale Invariant Feature Transform methodology. This registration is the motivation of our paper, no? In a generic way, the SIFT methodology, this second one, consists of the following 4 stages: feature selection, characteristics correspondence, features adjustment, and transformation. They are explained now, and I am going to show you in a pair, in 2 images, this situation. Here is the first of all, the preprocessing stage. First of all, we apply the median filter to the image. This is the original image. We apply median filter. Why we apply median filter? Because we treat to reduce the noise in this image, additive noise. It is an enhancement method commonly used for reduce the salt and pepper noise. Then we enhance this image with equalization of histogram. Here it now the image is better shown. And we divide in 3 channels. Every color image has 3 channels: red channel, green channel, and blue channel. The green channel, this one, is very similar to this image transformed to gray level, but with too much less noise. And if, in the fluorescent imaging, this is the entrance, the input. This is the result of median filter, and it is negated. Why we negate it? Because it is needed now. It is a result from our work. That is the reason of this paper, that here you can see the vascular part, this black, and they are here, they are white. Why we negated this image? Because we wanted that the image be in the same form, the vascular venous and arterial part be both of them of the same type. Here, feature selection. I have only 10 minutes for this explanation, but I am going a little hurry. This is the first feature selection. it is the process. Here is it explained this process. In that case, we get this parts, this green area showing. We are treating now to process both images, the fluorescent image and the optical image. After the preprocessing, applying the shift register methodology. During the key point detection process, the X and Y coordinates are stored where they were located. The last scale at which the key point was held is in turn identified and assigned as scale parameter. You can see in this part, this is the X and Y and angle and scale, because when both images from the same patient are get, it is probably they are not the distance from the eye of the camera is not the same, and maybe it is radiated one of them, the other not, the other one not. That is our problem, and we must both of them from both of them to get a new image fused. It is a fusion from two images. Here you can see some steps. We are processing these matrices. They have each point of the image of one image, and the second one all information about each pixel. After these 4 stages, we do also a characteristic correspondence, features adjustment, and transformation. Most now we are show some graphic experiment that clarify our purpose. Here is the input. Here from the optical image, the median filter, histogram equalization, and here a green channel. Here is the input of the fluorescent image. Here is the median filter. Here is negative. And now you can see that all arterial and veins are of the same, are not bright, but obscure. Here, feature selection from one and the another one. Afterward, we do the characteristic correspondence between them. You can see in this image, this point, it is very near to this one. They are compared, both images, and we are getting the differences of both of them. After the Euclidean correspondence, we also use the hook correspondence. You can see that it is the same. The objective is to get the difference between two images and get in our optic image the micron, the difference. They are the micron units. Here, adjust and transformation of the image to be registered on the image reference image. You can see. Here, reference image and image resulting from the transformation, and finally, both of them are the OR, logical OR of the image to be registered and the reference image. In this case, there is not a microaneurysm. We knew before of all. We can see here. Please. Where it is. here. Synchronically, without microanalysm. This is the optical. In this operation, it's possible to do from optical to fluorescenic or from fluorescenic to optic in both senses. Now, this is the error. You can see that the difference, the error, the coincidence of the microaneurysm, not to say, here is the value, a minimum square error is calculated. But here, for example, there is an image with microaneurysm. We do the same process, all of them, what this image has microaneurysm, here adjustment and transformation, and we get the OR image finally. Here you can see, here in these zones, that the microaneurysm are detected, are shown with the collaboration of both, the comparison with the correspondence of both images. The fluorescenic image where I saw everything, and the optical image where I didn't see anything. This is the error. Graphically, you can see there are coincidences, but some places that it was necessary to register the green point, and it was registered the result in this red circle. You can see not all were detected. Thank you so much. Our first, our main result that we applied pre-processing for get a good result. Without that, it would be very difficult to find the microaneurysm. Thank you.
Okay, Edgardo, thank you so much. Somebody have a question? Okay, Edgardo, this instance you were about the study of ACE in the people. In this image that you have, the image correspond a child, adults. Which one are your subjects, patient? Are childs, are adults?
Yes, we work only with images from adults, because in our projects, I am working with this more than 20 years. The main objective is to detect problems in retina from adult. In the little, for example, somebody which is too adult mainly present the problems, the affectation. I don't know, jóvenes. I don't know.
Okay.
What?
Yes, I understand. Thank you very much, Edgar.
You're welcome.
Yes, thank you very much, Edgardo. We're going to continue. With next presentation, that is clinical notes classification system for automated identification of diabetic patients. The authors, Jonathan Zavala, Juan Carlos Olivares, José Antonio Gutiérrez, Adriana Telles, Jesús Alcaraz, and Enrique Reyes. Don't forget, please remember 10 minutes for presentation and 5 minutes for question and answers. You can start. You can begin.
Okay, thank you. Can you see my presentation?
Yes, we see.
Okay. Good afternoon. My name is Jonathan Zavala. I'm from the Instituto Tecnológico de Morelia, and I will be presenting my work on clinical notes classification. So there is a lot of important information stored in patient electronic health records. Supervising medical information effectively is crucial in modern healthcare, and automating process for diagnosis chronic diseases is essential. So these notes from doctors, which have lots of details about patients' medical history and observation, are now really important information in healthcare. At the same time, diabetes, one of the most prevalent chronic diseases worldwide, requires effective management. When this motivation has a starting point for our doctoral project, where we require a set of clinical notes associated with patients with diabetes, we have created a binary classifier. This classifier uses a hybrid approach that combines rules, information extraction, and machine learning to efficiently identify clinical notes of diabetic patients. So after looking at different studies, we found some that use binary classifiers with clinical notes. Most of these focus on medical notes in English, and there are only a few in Spanish. In these studies, they compare different machine learning models, and support vector machines seems to work the best. This is the proposed methodology, is starting with corpus analysis, manual labeling of clinical notes, pre-processing, bag of words, and frequency analysis, definition of roles, and information extraction process, implementation of machine learning algorithms, and integrating roles, information extraction, and machine learning. So from the analysis of corpus, we extracted relevant information. When reviewing the number of words per clinical note, we observed that most of them were in the range of 200 words or less. By analyzing the frequency of words, we identified those that appeared most frequently. Also when searching of keywords related to diabetes, we noted which were the most frequent and proposed a label to group them. So our dataset comprises approximately 500,000 clinical notes from around 300,000 patients with various diseases. With the collaboration of the health professional and student from Tecnológico de Morelia, we labeled a set of 6,000 medical notes from diabetes patients and another 6,000 from non-diabetic patients. In the pre-processing stage, we clean the clinical notes and we remove accents, convert all the text to lowercase. Next, we used the NLTK library to tokenize the words in each clinical note, and we removed stop words. The bag of words matrix is organized as follows. Each row represents medical notes, while the columns contain the diabetes-related keywords. in the matrix, the frequency of these words in the medical notes is recorded. So we performing a frequency analysis to determine the number of diabetes-related keywords presented in the data sets labeled as diabetes and not diabetic. In the diabetic data set, no notes were found with 0 keywords, while approximately 5,000 notes in the non-diabetic data set had 0 associated keywords. In the data set, labeled diabetic, we observed that the word diabetes was the only one that appeared exclusively. Also, in the dataset labeled not diabetics, we noted that the word glucosa was the only one found most frequently, standing out largely exclusively. Based on the previous analysis, we have established the following rules. If we don't find any keywords, we label the node as non-diabetic. So if we find only one keyword, we present the node. And the third rule is especially if the keyword is glucose. The next phase involves looking for explicit information in the node. In the A1, we are looking for evidence that contradicts the condition of diabetes, while in A2, we focus on looking for the diagnosis of diabetes. So in the integration of rules, information extraction, and machine learning, we propose the following flow. The first rule, if keywords is equal to 0. The second rule, if keywords is equal to 1. So the first structure information that if the condition is DINET, the third rule, if the keyword is glucosa, and the A2, if this condition is affirmed. So in this part, the clinical node is labeled like a possible diabetes. So in this part, we implemented machine learning algorithms. This is all our results. So we implemented four models, support vector machines with accuracy of 0.99, logistic regression and random forest, and with the best performance, gradient boosting with 99%. So we implemented with validation data for diabetic labeled another data set with no diabetic, and an external data set with odontology clinical notes. For us is the no diabetic, the supported vector machines with 99%, and the best performance average gradient boosting. So in the final part, we combined the rules with information extraction and with the model. For the data set, of diabetic, all of them with the best precision. And for the non-diabetic data set, this combination will have the best performance. So for the data set of oncologic, for us, non-diabetic, logistic regression combined with the rules and information extraction, we have the best performance and the best average result, the random forest combined with rules and information extraction. The conclusion in the first analysis, the first algorithms evaluated showed similar performance, handling the gradient boosting with a precision of 99%. So these algorithms were evaluated in our own level clinical nodes and in a database of oncologic nodes. In the latter case, the support vector machine algorithm demonstrated a highest accuracy by correctly labeling the nodes as non-oncological with 99%, and at the same time, gradient boosting obtained the best overall average with 96%. Combining the three techniques, including rules, information extraction, and random forest, yielding the best average performance. The combination significantly improved the classification of clinical nodes, reducing the margin of error in the identification of nodes from diabetic patients. There are my reference is all for my part. Thank you.
Thank you so much, Jonathan. Somebody have a question?
Yes, I have just a little question.
Yes.
It's about the dataset. Can you explain a little bit more about the dataset? I know that you explained that it was clinical notes, but a little bit about how do you get it? And each clinical note have a corresponding diagnostic of diabetic or not diabetic? Thank you.
Okay. Yes, this data set, por aquí tenía, okay. This data set is about of several diseases. No, it's only of diabetes. En esta parte, no, 1 minute. Okay. Okay. This part is for about 500,000 clinical notes from patients with various diseases. In this part, these clinical notes they are not labeled. So for this data set, we labeled some of their 700, 7,000. So in this database, only we have the clinical notes in narrative format, so it was necessary to convert in TXT format. It's only the information that we have, only the clinical notes.
Thank you.
Thank you. Thank you. Jose Eduardo, somebody wants to be inside with us to check, please. Somebody have another question? Okay, we're going to pass to the next work. Hyperparameter optimization approach to improve the performance of machine learning model for cardiovascular risk prediction. The authors, Eduardo Sánchez, Alejandra Cuevas, Yasmín Hernández, Javier Ortiz, Alicia Martinez, and Hugo Estrada. Don't forget, you have 10 minutes for presentation and 5 minutes for a question and answer. You can begin.
Yeah. Are you listening?
Yes, we can.
Yeah. I was the one that I was asking for the permission because I couldn't access with my computer, but it's okay. I will start. Good afternoon. My name is Alejandra Cuevas from Centro Nacional de Investigación y Desarrollo Tecnológico, also known as CENIDET, and I will be presenting the following paper called Hyperparameter Optimization Approaches to Improve the Performance of Machine Learning Models for Cardiovascular Risk Prediction by Sanchez Jimenez et al. This presentation has the following order: the introduction, the hyperparameter optimization in machine learning classifiers, materials and methods, the discussion and analysis of the experiments, and finally the conclusions. We call the process of machine learning model building complex because it takes time to get the optimal and appropriate model when the focus of the performance model relies on the parameter configuration. There are two types of parameters that can upgrade the performance of the classifiers, those that can be initialized and updated through the training process, and those called hyperparameters that must be set before training a machine learning model. Hyperparameters optimization automates the hyperparameter tuning process and enables users to apply machine learning models to real-world problems. It also improves the classifier's performance. And in this paper, we use three approaches: Bayesian optimization, particle swarm optimization, and genetic algorithm. The first one finds the maximum and minimum of an expensive and unknown function by iteratively balancing exploration and exploitation based on Bayesian inference. The second one is inspired by social animal behavior and simulates the movement of the population called particles through a solution space, aiming to find the optimal solution. The third, inspired by natural selection, evolves a population of potential solutions over multiple generations, improving the solutions and aiming to find an optimal or near optimal solution to a problem. We apply three classifiers: random forest, support vector machine, and extreme gradient boosting. The hyperparameters we focus on tuning for random forest were n estimators, criterion, max features, max depth, mean sample split, and mean sample slip. For example, n estimators are the number of decision trees considered for training the model, and max depth is the maximum depth of each decision. For the support vector machine classifier, we focus on the hyperparameters C, kernel, degree, gamma, and coef 0. Kernel determines the types of decision boundary used to separate the classes in the input space. Meanwhile, degree determines the complexity of the decision function and the ability of the model to fit the data. For XGB boost, the hyperparameters we focus on were n estimators, learning rate, gamma, subsample, max depth, and call sample by tree. Learning rate controls the speed at which the model learns for previous mistakes and adjusts the weight of the trees. Subsamples, on the contrary, determines the proportion of instance to consider for each tree. The methodology we propose begins with preprocessing the data set. We treat the missing values and the outliers. We scale the data and divided this data set into training and testing. Then in the training data, we use the three classifiers, random forest, SVM, and XGBoost. Then we apply the three hyperparameter optimization approaches, Bayesian optimization, particle swarm optimization, and genetic algorithm to search for the best hyperparameters. In the testing phase, we obtain the performance of the three models, additionally to the default one, through the confusion metrics and the evaluation metrics, accuracy, precision, recall, specificity, F1 score, and ROC. If we noted that the performance did not improve, we search again for the optimal hyperparameters through the three optimization approaches. Once we obtain the results, we analyze them and select the best model for the dataset. The dataset we use was Framingham, which predicts if the patient will develop her disease in the next 10 years. It contains 7 binary attributes, 8 numeric, and 1 ordinal between demographic, medical records, and lifestyle data. We identify missing values completely at random, which we impute using the mean for quantitative attributes and the mode for qualitative ones. We treat the outliers by applying winsorization, and for the imbalance problem, we use Hadacin. 3,596 instances are classified with no risk for developing heart disease in 10 years, while 644 instances are labeled as risk for developing heart disease in 10 years. After we resampled data, the instances were equally balanced, 3,596 for each target label. And finally, we use robust scalar as a standardization technique. The search space we defined for the three classifiers and the three parameter approaches was focused on ROC metric as the objective function. We also defined it by previous experience, and in some cases, the value varied between hyperparameter approaches. For the case of the kernel by SVM, we search between linear, poly, radial basis function, and sigmoid. Approximately 6,972 instances were used for the training phase, while 220 were reserved for the evaluation phase. We observe on the screen the confusion matrix results. The last column on the right represents the correctly classified instance, and the classifier and hyperparameter optimization approach that obtained the most correctly classified instance was XGBoost and HBM with Bayesian optimization. On the contrary, the less correctly classified instance were by SVM with the genetic algorithm approach. If we focus on the accuracy metric, the best performance was obtained by SVM and XGBoost with Bayesian optimization. However, if we compare the performance obtained for the default configuration with SVM as the classifier, the model improved from 76.36% to 95%. For XGBoost, the model improved from 90.91% to 94.09%. If we want to focus on the data label with the risk of developing heart disease, the performance of the recall metric increases from 74.77% to 96.56%. 40% with SVM, and practical swarm optimization and genetic algorithm approach. In general, we notice a positive increase in the performance of the machine learning models. The following tables contain the basic parameter configuration for the 3 classifiers and the 3 parameter optimization approaches, in addition to the default configuration. We can notice, for example, that random forest for Bayesian optimization and particle swarm optimization doubles almost the n estimators compared to the default configuration. For SVM, the kernel was the same for the 4 approaches, and the degree hyperparameter is null because the kernel must be poly instead of radial basis function. XGBoost obtained almost the same results as random forest is in n estimators, but max depth double and tries the values from 6 as the minimum and 23 as the maximum. We concluded that optimization approaches improve the evaluation metrics by transforming the predictive ability of classification. And also the optimization approach choice depends on the dataset and the model complexity. Both Bayesian optimization and genetic algorithm approaches improve the accuracy, specificity, and recall metrics. SVM obtained the best performance in accuracy and specificity metrics, categorizing correctly both positive and negative instance. Finally, XGBoost excels in the retrieval metric, identifying accurately positive instance. We can begin with the questions. That it's all from me.
Thank you so much. If somebody have a question, this is the moment. Did you hear to me?
Yes.
Did you listen to me? I have a question. How you choose the algorithm of classifications? I see 3 algorithms. I want to know how you choose these 3 algorithms.
Okay. We did experiments previously with this dataset with some classifiers as AdaBoost and decision tree. And from previous experience, we decided that we only took the first 3 classifiers with the best performance.
Okay, I understand. It was according to previous experiment. Thank you so much. We're going to pass with next work entitled Identification of Gynecological Pathology by Applying Classification Algorithms, Results of a Local Study. The authors are Eddie Sánchez, Mirta Fuentes, Cecilia Loesa, and Irajan Otoniel. We can begin. Don't forget, you have 10 minutes for presentation. Next, 5 minutes for question and answers. You can.
Can you see my presentation?
Yes.
Thank you so much. Thank you for the opportunity to present our results. I told about our research work entitled Identification of Gynecological Pathologies by Applying Classification Algorithms, Results of a Local Study. The authors in this paper are listed from the National Technological of Mexico, Campus Misantla. we focus on classified data originated from vaginal pathologies records. The presentation will have these contents, background, materials and methods, results, findings, and future work. The motivation for this work is that in Mexico, vaginal infections are common in women between 20 and 45 years old. So the early diagnosis of gynecological disorders is essential. There are different factors that can influence on these infections, such as bacterial infections, unprotected sex, altered physiological processes, lifestyle choices. Therefore, we analyze classification algorithms in vaginal pathologies. The problematic is that vaginal infection is one of the most frequent causes of gynecological pathology consultations, and to identify a pathology, an inferential process is carried out, performed from a medical condition, which refers to a concept specific to medicine and consists of a physician's assessment of the patients and considering different symptoms of a patient and clinical signs. This can lead to an accurate diagnosis or a presumptive diagnosis, which must corroborated later and in some cases with other studies such as analysis, radiographs, magnetic resonance, among others. This analysis could be complemented with the use of computational tools. However, in the region of Tabasco, there is still a lack of diagnosis supported by intelligent software. Hence, we implemented and evaluated the performance of 4 machine learning algorithms to identify cases of vaginitis. Hence, our contribution is using computational techniques to classify vaginitis records. Specifically, we employ machine learning classification algorithms, and this work is established in the domain of experimental machine learning. Our proposed solution is the following. To implement simple perceptron, naive-Bayes, CAR, and AdaBoost algorithms to identify vaginitis 4 types: Gardnerella, candidiasis, trichomoniasis, and chlamydia, in 600 records of patients in southern Mexico. Now we will see the materials and methods used in this work. To carry out the experiments, we acquired records from the Villahermosa Tabasco Women's Hospital corresponding to the symptoms presented in vaginal infections, such as flaws, secretion, irritation, painful urination, among others. The age data was not considered in the data set, since the pathologies are not related to the age. Even girls can contract any infection from using public bathrooms. The vaginal pathologies that we identified were Gardnerella, candidiasis, trichomoniasis, and chlamydia. Historical records were divided into files with comma-separated values. 10 data sets were constructed consistent on binary classification corresponding 2 different vaginal infections. With the collected data, we generate 10 data sets using 2 strategies. The first, 1 versus 1, and the second, 1 versus all. The 1 versus 1 is simple. Imagine that you have several classes, such as dogs, cats, bears. With 1 versus 1, we create a classifier for each pair of classes. For example, one only for dogs and cats, another for dogs and bears, and so on. This simplifies the decisions. On the other hand, 1 versus all, we chose one class at a time, say dogs, and trying to classify to distinguish them from the rest, cats, bears, among others. Then we do the same for the other classes. It's like saying, are you a dog or not? And repeat this for each category. Using these 2 strategies, we generate the data sets that shown in table. You can see the picture, the identification of vaginal pathologies process, which consisted of data acquisition, dataset construction, algorithm implementation, and identification of vaginal pathologies. We employ Python. A personal computer with Windows operating system of 64 bits, Intel i3 processor, and 8 gigabytes RAM were used. Also, Python was used to implement machine learning algorithms and use some packages, NumPy, scikit-learn, and pandas. Now I will comment on the results obtained. As shown in the table, for each dataset were obtained the respective percentage of correct classification of accuracy. The algorithm simple perceptron achieved 100% with the datasets 2, 4, 5, and 8, while CAR algorithm and AdaBoss achieved 100% with the datasets 1, 2, 4, 5, 6, 8, and 10. On the other hand, the worst performance was obtained with the naive-based algorithm. Now I will show the conclusions. The focus of this study was to propose to implement and assess the performance of 4 machine learning algorithms to identify vaginitis cases in the south of Mexico, in Villahermosa, Tabasco. Through the experiments, it was possible to find promising results in terms of diagnostic accuracy with algorithms such as CAR and AdaBoss, achieving classification rates above 90% in most cases. Also, the ability of these algorithms to diagnose vaginitis with high accuracy has a potential to improve medical care by enable early and accurate diagnosis. Also, we expect that these results can help to construct a front-end software supported by back-end machine learning algorithms. As future work of this research is considered, include other attributes, explore if it's possible to get the same accuracy or best performance with fewer attributes, get data from another hospital to have more medical records, and develop an expert system for functional use in health centers where there is not an specialist doctor. It's all for the presentation. Thank you for your attention.
Thank you so much for this presentation. If somebody have a question, okay. Cesar?
Good afternoon, Cecilia and research. Congratulations for your work. I have a question. Are the data of this project available?
Yes, and the data set is available on the request on the corresponding author. The email is in the presentation.
Thank you.
Yes, another question. What clinical feature do you use for the model construction?
Are they listed in the table, flow, secretion, and among others?
These are all the features you use, ¿verdad? Flow,
Yes,
secretion.
yes, they are.
Thank you.
You're welcome.
Okay, somebody more? We have no more question. Thank you so much for this last presentation. In this moment, we're going to give the word to Jose Eduardo. Jose Eduardo is finished this session. ¿Algún administrador aquí en de la
Sí, doctor.
sesión?
Sí, pues muchas gracias. Thank you so much for your assistance. And that's all for today. Thank you so much for your presentations and hope to see you again in another workshop. Thank you so much.
Thank you, everybody. Good afternoon.
Good afternoon. Goodbye.